Welcome, fellow travelers, to our exploration of the cosmos. For millennia, we've gazed at the night sky, driven by curiosity. What are those lights? Where did we come from? Where is it all going? This journey is about understanding our place in the universe, connecting the atoms in our bodies to the stars above. Our adventure takes us beyond Earth, into the vast darkness between galaxies where wonders await, star-forming nebulae, ancient clusters, and the mysterious pull of black holes. Each discovery brings us closer to answering humanity's oldest questions. We're not just observers, we're participants, using powerful telescopes to look back in time and witness the universe's youth. Today, we stand at the edge of a new era, ready to tackle one of science's biggest mysteries. Our journey begins with a simple, world-changing observation. Everything is moving away from everything else. The universe is expanding, a fact that opened a Pandora's box of cosmic questions. Let's step into this expanding reality and explore the mystery that awaits. Picture baking raisin bread. Every raisin moves away from the others as the dough rises. That's our universe. In the 1920s, Edwin Hubble discovered that the farther a galaxy is, the faster it moves away. Not because we're at the center, but because space itself is stretching. This led to the Big Bang theory. The universe began from a single, hot, dense point and has been expanding ever since. Astronomers measured this expansion rate, the Hubble constant, and thought they understood the universe's history, but a problem emerged: the Hubble tension. Predictions from the early universe don't match direct measurements today. The numbers just don't add up. It's as if your car's speedometer disagrees with the engine specs, a significant, not minor discrepancy. This tension suggests our standard model of cosmology is incomplete. Maybe the universe expanded differently, or there's a new force or particle at play. Solving this puzzle is urgent. It could reveal a universe stranger than we imagined. The Hubble tension is more than a problem, it's a clue to a deeper reality. For decades, cosmologists thought gravity would slow the universe's expansion, maybe even reverse it. But in the late 1990s, astronomers found the opposite. The expansion is speeding up. It's as if you threw a ball upward, and it accelerated away instead of falling back. This shocking discovery led to the idea of dark energy, a mysterious force pushing space apart. Dark energy makes up about 68% of the universe, yet we have no idea what it is. It acts like anti-gravity, dominating the cosmos while remaining invisible. The nature of dark energy is science's greatest mystery. Is it a constant property of space, or does it change over time? The answer will determine the universe's fate: endless acceleration, or something even stranger. If dark energy is constant, expansion continues forever. If it changes, anything is possible. Understanding dark energy isn't just about the Hubble tension, it's about predicting the end of time itself. The stakes couldn't be higher. To solve these mysteries, we need a revolutionary tool, the Vera Rubin Observatory. Perched in the Chilean Andes, it's not just another telescope, it's a next-generation survey machine. Named for Vera Rubin, who helped reveal dark matter, this observatory will transform our cosmic understanding. Its heart is a massive 8.4-meter telescope, and the largest digital camera ever built for astronomy. 3.2 gigapixels, the size of a small car. It can capture an area of sky 40 times the size of the full moon in one shot. The Rubin Observatory will survey the entire visible southern sky repeatedly, creating a time-lapse movie of the universe. Its main project, the Legacy Survey of Space and Time, LSST, will scan the sky every few nights for a decade. It will catalog billions of stars and galaxies, but more importantly, it will capture change, anything that moves or flashes. This relentless survey is exactly what we need to tackle dark energy and the Hubble tension. By mapping the universe in 3D, the LSST will provide the most precise expansion history ever. The Rubin Observatory is our new eye on the cosmos, ready to reveal a universe we've only dreamed of. How do you measure distances across billions of light years? You need a standard candle, an object with a known brightness. In astronomy, that's the type Ia supernova, a white dwarf star in a binary system that explodes at a precise mass. These explosions are remarkably consistent, making them perfect cosmic mile markers. By comparing a supernova's known brightness to how dim it appears, we calculate its distance and that of its host galaxy. This method is one of our most powerful tools for mapping the cosmos. It was Type Ia supernovae that led to the discovery of dark energy. Distant supernovae were dimmer than expected, revealing cosmic acceleration. With the Rubin Observatory, we'll find these standard candles in unprecedented numbers. This will give us the data to map the universe's expansion with exquisite precision. Each new supernova is a data point in the story of cosmic evolution. The more we find, the clearer our picture of the universe's fate. The Rubin Observatory will revolutionize our understanding of distance and time. The universe's secrets are about to come into sharper focus. The LSST isn't just about pretty pictures. It's a 10-year campaign to create the deepest, widest movie of the night sky. Every few nights, the Rubin Observatory will capture torrents of data, building a data set of staggering scale. By the end, it will have cataloged an estimated 37 billion stars and galaxies. The survey has 4 main goals: probing dark energy and dark matter, inventorying our solar system, exploring the transient sky, and mapping the Milky Way's structure. By observing how galaxy light bends around invisible mass, LSST will create a 3D map of the dark universe. It will also discover thousands of new asteroids and comets, helping us understand our solar system's origins. The LSST will catch cosmic events as they happen: supernovae, flaring stars, colliding neutron stars, generating millions of alerts each night. It's like a cosmic security camera always watching. By mapping our galaxy's history, we'll see the remnants of ancient collisions and trace the Milky Way's evolution. The LSST is a legacy for generations, a treasure trove for future discoveries. The Rubin Observatory will unleash a torrent of data, 20 terabytes every night, over 60 petabytes in a decade. No human team could sift through it all, so we turn to artificial intelligence and machine learning. Each night, the observatory will generate 10 million alerts, potential discoveries that need instant classification. Machine learning algorithms like the Think program will analyze each alert's properties and compare them to vast libraries of known objects. Within minutes, the system will classify events: supernova, variable star, or something new. This real-time analysis transforms astronomy from reactive to proactive. Discoveries come straight to researchers. Scientists can follow up on fleeting cosmic events almost instantly, capturing them as they unfold. This synergy between big data, AI, and human curiosity is a generational shift in how we explore the universe. The future of discovery is automated, rapid, and global. With these tools, we're ready for whatever the universe throws at us. The Rubin Observatory's data will usher in a new golden age of cosmology. For the first time, we'll have a data set big and precise enough to truly test our theories. By analyzing millions of Type Ia supernovae, we'll map the universe's expansion in unprecedented detail. We may finally answer, is dark energy constant or does it evolve? The answer will reshape our understanding of physics and the cosmos's fate. If dark energy changes, it could mean a future big rip or something even stranger. The observatory will also let us test Einstein's theory of gravity on cosmic scales, searching for cracks in our understanding. The greatest discoveries may be the ones we can't predict: new explosions, unknown phenomena, surprises lurking in the data. The future isn't just about refining numbers, it's about discovering the unknown unknowns. The Rubin Observatory is our new map, and on its edges there will surely be dragons. Why do we build observatories on remote mountaintops? Because exploring the universe is fundamental to who we are. The quest to understand the cosmos is driven by the same curiosity that led us to explore continents and peer into atoms. Looking up connects us to something larger, giving us perspective and humility. Astronomy reminds us our world is a small, fragile stage in a vast arena. The discoveries ahead with the Rubin Observatory belong to everyone. The data will be public, inspiring scientists, educators, and dreamers worldwide. The technology developed for this project drives innovation that benefits society in countless ways. Ultimately, we look up because the universe is the grandest story, and we are part of it. The elements in our bodies were forged in ancient stars. We are the universe's way of knowing itself. The quest to map the cosmos is a quest to understand ourselves. The night sky is full of mysteries, and with each discovery, the universe invites us to look deeper and continue our cosmic journey.